Hey kids, so we are doing our thermochemistry uh, unit, and the thermochemistry unit has to do with heating and cooling. But cooling, it turns out, is just a matter of taking energy away from something, and then heating something is putting that energy back in. And that energy allows for either kinetic energy to increase or for some phase change to occur. And that is what we talked about, and basically how things go from a hotter, more heated substance to a less heated substance. That heat travels in that direction. Um, that's the way heat travels. And then if you take heat away, then energy travels away from the. See, now this one, the brick is now cooler, and so heat is traveling to it from the iron, trying to get it back to hot, and then ultimately the iron will cool off as well because the brick is losing its heat, its energy to the ice. All right. So, having said all that, let's talk about this unit. So, the definition of heat is energy transferred between objects at different temperatures, and temperature is the average kinetic energy of a substance. So, the key here is that heat is energy transferring, and temperature is more of a measure of how much things are moving. The symbol in equations for heat will be Q, and for temperature will remain T. So Q, not exactly intuitive, but temperature as a T, hopefully. And since we just did that with PV equals nRT stuff, that won't be a surprise to you. The unit of measurement for heat is joules or kilojoules, and for temperature is degrees Celsius or Kelvin. And we have to calculate heat. If I ask you about heat, it's something you have to calculate, whereas temperature you can measure with a thermometer. So heat goes one way in one direction. It goes from objects with higher temperature to objects of lower temperature. And if two objects remain in contact, the heat will flow from the one into the other until they reach what's called an equilibrium, which means they're both at the same temperature. So that energy will transfer in between from the hotter of the two substances to the less heated one. And when the temperature of both substances are the same, that's when the heat will kind of equilibrate. Um, the object or substance that gains heat would have a positive value for Q, and one that loses heat will have a negative value for Q. All right, so we talk about specific heat, and the quantity of energy transferred as heat during temperature change depends on the kind of material, the mass of the material, and the change in the temperature. As you saw before, the brick could only hold a handful of energy units, not near as much as the iron. That's because iron had a higher specific heat. It could hold more heat per gram of iron. And specific heat is the amount of energy required to raise the temperature of 1 gram of substance, 1 degree Celsius, or 1 Kelvin. The units of that, therefore, would be the amount of energy, joules, per gram per degree Celsius. So joules per gram degree Celsius. Written also as, uh, so joules per gram degree Celsius, like that. All right. So here are some substances specific heats. And what we see here, here's a high one, 4. 2 is a high one. 2 is a high one, right? And then there's some low ones here, 0.129 and 0.140 mercury liquid. So what does a high specific heat mean? A high specific heat means it's going to take a lot of energy to raise 1 gram, 1 degree Celsius, right? So, for example, liquid water is going to take 4.18 grams, joules of energy to heat 1 gram of liquid water, 1 degree Celsius. It also means it's going to take a lot to lose that heat. So, that is something else you got to consider. That water will hold 4.18 joules per gram, and to lower its temperature by 1 degree Celsius, you're going to want to take that much energy out. So a low specific heat means the opposite. It will heat up quickly. So gold foil would heat up quickly. Every gram of it would only need 0.129 joules of energy to go up a degree Celsius, and it would also cool down quickly. That you just need to lose 0.129 joules of energy to cool it down a degree Celsius for every gram. So the calculations for this are using this equation that heat equals mass times the change in temperature times the specific heat, where Q again is heat. It'll be negative when heat is lost and positive when heat is gained. M is mass, Cp is specific heat, and the delta T is a change in temperature. If you're worried about, and I don't think I'm going to get into it too much, the positive negative thing, T final minus T initial will always give you the right sign for the heat. And now we need to do some problems. So in this problem, you have 50 grams of iron and you're heating it from 20 to 80 degrees Celsius. The specific heat of iron is given as 0.449 joules per gram degree Celsius. So we just plug everything into this. 50 grams times the change in temperature. So 20 to 80, that's a difference of 60 degrees. And then your specific heat is 0.449. So you multiply all that and you get the heat being 50 times 60 times 0.449, 1347 joules is how much heat was required to make that happen. So for this next question, we have 566 joules of heat. Cools copper from 77 to 22. What was the mass of copper? And we can do something like this maybe actually this week. So if you have 566 joules, and that's going to equal the mass, which we're trying to find out, the change in temperature was 55 degrees, and your specific heat was 0.385. So what we're trying to do is solve for M. So 55 times 0.385 is 21.17 or 21.18. So 21.18 M is equal to 566 joules. Solving, isolating M, you go 566 divided by 21.18, and you get 26.7 grams, which is what M is equal to. All right. And then we got into heating curves, which I will start on the next slide.